Hello. Today we'll see how block ciphers and iterated hash functions can be used to construct two MAC schemes, CBC-MAC and HMAC. I'll first show you how MAC schemes can be constructed from block ciphers. This construction is CBC-MAC, CBC standing for cipher block chaining, as was used in CBC mode of encryption. Let E be an n-bit block cipher with L-bit keys. I'll assume that plaintext messages have lengths that are multiples of n. If not, then we would add some padding to the message. To compute the MAC of the message X, we'll divide X into n-bit blocks X1 through XR. We'll then encrypt the first message block X1 using the key K to get H1. And then we'll recursively encrypt the previous block HI-1 plus the next message block XI to get HI. The last block HR is defined to be the tag of the message X. The intuition for security is that the encryption process does a good job of mixing up the bits of the plaintext blocks and the secret key. So in the end, the tag of X is a very complicated function of the bits of the message blocks and the bits of the secret key. CBC-MAC comes with a rigorous security analysis from 1994. Here's an informal statement of a theorem. Suppose that the block cipher E is an ideal encryption scheme. In other words, for each key K in the key space, the encryption function EK is a random permutation of the block space. Then, CBC-MAC with fixed length inputs is a secure MAC scheme. So CBC-MAC is provably, existentially, and forgeable against chosen message attacks. As with all security theorems, the conclusion is very appealing. However, the hypothesis is also very strong, namely that the block cipher is ideal. You might have noticed that the theorem has a restriction on CBC-MAC, namely that it only allows fixed length inputs. This condition is necessary because CBC-MAC is not secure if variable length messages are allowed. Here is one chosen message attack on CBC-MAC that illustrates this claim. Select an arbitrary 3-block message X, whose blocks are X1, X2, and X3. Obtain the tag T1 from Alice or Bob of the 1-block message X1. By definition of CBC-MAC, T1 is the encryption of X1. Next, obtain the tag T2 of the 2-block message whose first block is T1 plus X2 and whose second block is X3. By definition of CBC-MAC, T2 is equal to this quantity. Finally, we'll observe that T2 is also the valid tag of the 3-block message X. The correctness of this claim is given here. One might question whether this attack is realistic. Nonetheless, it illustrates that CBC-MAC does not meet our very strong notion of security, namely existential unforgeability against chosen message attack. There are several ways to prevent the attack on CBC-MAC when variable length messages are permitted. Here is one such way, called encrypted CBC-MAC or EMAC. To compute the EMAC tag of a message X, one first computes its CBC-MAC tag using a secret key K, and then encrypts the resulting CBC-MAC tag using a second secret key S. So more concisely, the EMAC of a message X, where the secret key has two components, K and S, is the encryption under S of the CBC-MAC tag of the message X. EMAC has a rigorous security analysis from the year 2000. Here is an informal statement of a theorem. Suppose that E is an ideal encryption scheme. Then EMAC is a secure MAC scheme for inputs of any lengths. Recall that hash functions are unkeyed primitives, and so If we want to use a hash function to construct the MAC scheme, we need to specify how the hash function can be used to mix up the bits of the message and the secret key. There are several ways one can do this. I'll show you two methods for iterated hash functions. The hash function could be MD5, SHA-1, SHA-256, or one of the other hash functions in the SHA-2 family. So, let H be an iterated n-bit hash function, and I'll assume, for simplicity, that the length block has been omitted. The compression function f in H maps bit strings of length n plus r to bit strings of length n. For SHA-256, n is 256, whereas r is 512. The secret key is a randomly selected n-bit string k. I'll let capital K denote the message block you get by appending zeros to the left of the secret key little k to get a block of length r bits. The secret-prefix method is one way to construct the MAC scheme from an iterated hash function. The tag of a message X with secret key k is defined to be the hash of the concatenation of the key block k and the message X. Here is a diagram of the secret-prefix method. The key block and the blocks of the message are compressed one at a time with the compression function f, and the last output block is defined to be the tag of the message X. The idea is that since the adversary does not know the key block k, she cannot compute the tag of any message X of her choice. Nonetheless, the secret-prefix method is insecure. There is a so-called length extension attack which demonstrates insecurity. Suppose that the adversary knows the tag of a single message X. Then, without knowing the secret key k, the adversary can compute the tag of any extension of X. So for any y of the adversary's choosing, she can compute the tag of the message X concatenated with y. I'll demonstrate this next with one-block messages X and Y. Suppose that the adversary knows the tag T for a one-block message X1. So T is given by this expression. The adversary then selects a one-block message Y, computes T primed by compressing T and F, and defines X primed to be the two-block message X1Y. She outputs the message tag pair X primed T primed. Then you can check that T primed is indeed the correct tag for the two-block message X primed. The most commonly used MAC scheme today is HMAC. HMAC is hash-based MAC, designed by Bellari, Canetti, and Krawchuk in 1996. Define an r-bit string IPAD to be the single byte 36 repeated r over 8 times. Similarly, define the r-bit string OPAD to be the byte 5c repeated r over 8 times. These bytes 3, 6, and 5c were arbitrarily chosen. The important thing is that they are fixed and different from each other. The HMAC tag of a message X with secret key k is then defined as follows. You first add the secret key block k to the block IPAD and append the result to the left of the message X. This string is then hashed using the iterated hash function H. H could be MD5, SHA-1, or SHA-256. Then, the secret key block is added to OPAD, and the resulting block is appended to the left of the previous hash value. This two-block message is then hashed with H, and the resulting hash value is the tag of the message X. Observe that the main part of the HMAC algorithm is just the secret-prefix method, which is highly insecure. However, since the key block is appended to the left of the resulting hash value, and then this two-block message is hashed once more, the length extension attack is prevented. Here is an informal statement of a theorem. Suppose that the compression function f used in the iterated hash function h is a secure MAC scheme where messages are of a fixed length and a randomly selected IV is a secret key. Then HMAC is a secure MAC algorithm. As with other security theorems, the conclusion of the theorem is very appealing, namely, a mathematical guarantee that HMAC is existentially enforgeable against chosen message attack. However, we have a rather strong hypothesis, namely that the compression function itself is a secure MAC scheme. And hence, the theorem is only a conditional guarantee for the security of HMAC.
In practice, one should use HMAC with the SHA-256 hash function. HMAC has been standardized by NIST in FIPS 198. It's also standardized by the Internet Engineering Task Force, IETF, Working Group. IETF is a very influential standards organization that develops standards for the Internet.
HMAC is commonly used as a key derivation function, or KDF. Suppose that Alice has a secret key K, perhaps one she shares with Bob, and wishes to derive several session keys to encrypt data in different communication sessions. In practice, it's recommended that Alice and Bob do not use the same secret key to encrypt a large amount of data. This is because if an adversary somehow learns a secret key, then the adversary could decrypt a large amount of data. So, it's desirable for Alice to compute session keys from a fixed secret key K, protect K with great care, and use session keys derived from K to encrypt messages in different communication sessions. One way to compute session keys from a secret key K is to compute the HMAC tags of a counter using the secret key as the HMAC key. So Alice computes the first session key by computing the HMAC tag of 1, the second session key by computing the HMAC tag of 2, and so on. The rationale for security is that without knowledge of the secret key, an adversary is unable to learn anything about any particular session key SKI, even though the adversary might have learned some other session keys. And this is because HMAC is existentially enforgeable against chosen message attack.
I'll conclude the discussion of HMAC by letting you ponder the following deep question. What is the difference between HMAC and a Big Mac? HMAC is easier to digest. Tee-hee. Having studied symmetric key encryption in Chapter 2 and MAC schemes in Chapter 4, we're ready to combine them to get authenticated encryption schemes. Authenticated encryption schemes provide both confidentiality and authentication services. I look forward to seeing you in V4b.